Hey guys, so let's talk about chapter 2 and the second section on water and why water is just awesome and how we need it and it's super important. So let's begin on just its shape. Remember, we talked about in the previous video about chemical bonds and covalent bonds and ionic bonds and hydrogen bonds, and water had covalent bonds between the hydrogens and the oxygen, right? Yeah, the little hydrogens and our oxygen. That looks terrible, but we're just going to pretend that it looks good. and with those chemical bonds and those ions passing back and forth, the electrons passing back and forth between the hydrogen and the oxygen, it's sharing it. So it's a covalent bond, but remember, it shared it unequally. So the oxygen kind of hogged it more than the hydrogen did because it's bigger and it has more protons to attract that electron. So it was polar, meaning that it has poles. It's a slightly different charge on one end of the molecule versus the other. So we're going to have slightly positive end over here and a slightly negative end over here. And that means it's polar. So it's covalent charge. It's a covalent bond. They are sharing that electron back and forth between the two atoms. It's sharing, um, but it's sharing unequally. So it is polar covalent bond. And because it has that shape, that is part of the reason why water is so amazingly cool. Water is that polar shape. It is going to attract molecules that are also charged, that slight charge. So anything that bonds with water that can dissolve in water is going to be hydrophilic. And hydro, water. Philly means love, right? Philadelphia is a city of love. Hydrophilic means it loves water. So things that will bond and break apart in water, like um, anything that will dissolve in water, salt, sugar, all of those molecules that break apart in water are hydrophilic. But there's some things that never mix with water, right? There are things that are never going to bond with water, and we can see it in this picture right here. And those are hydrophobic. They fear water. They don't like water. They never go and bond with water. They're never friends. So oil and water. Oil is a type of lipid. We're going to get into the macromolecules in the next video. So lipids, oils are hydrophobic. Absolutely, they are not going to bond with water, no matter how polar and beautiful looking it is. It doesn't care. So if it's hydrophobic, it doesn't bond. If it's hydrophilic, it will bond with water. So we're going to talk about hydration spheres for those hydrophilic molecules in just a little bit. We'll see a picture of those guys. But here's another really cool trait about water besides being polar. It is going to have a very high heat capacity. This high heat capacity is going to help stabilize the temperature in its area. So the molecule of water, and we talked about how it's the covalent bonds between the hydrogens and the oxygen. And then when one molecule of water is bound to another molecule of water, we had these bonds, right? And these bonds were the hydrogen bonds, and they were kind of a temporary bond. It's not like the covalents that's pretty rock solid when they share that electron back and forth. The hydrogen bonds can break apart depending on what's happening to the molecules. So if the water gets heated, you are trying to make boil a pot of water at home, trying to make spaghetti or ramen or whatever, you're trying to boil that pot of water to make whatever you want to make. And the more heat you put into it, eventually that pot of water will boil. Eventually, even if you stare at it. So it takes a lot of energy. The fact that it takes a lot of energy to change the temperature of water means it has this high heat capacity. It takes a lot of energy to break these hydrogen bonds. And when they finally break, they're going to change from a liquid to a gas. They're going to vaporize, they will evaporate and become a gas. And that takes a lot of energy when that happens. So, any of us, when we get hot, we sweat, right? That's your body's form of cooling itself down. One of a few things that helps your body cool down. And so, when you sweat and that sweat is formed and then it evaporates away, it cools you down because, again, getting that water to transfer from a liquid to a gas takes a lot of input for it to transfer from a liquid to a gas. So, these guys, high heat capacity to break the bonds between the molecules, to break all these hydrogen bonds and allow the water molecules to go from a liquid to a gas and evaporate. So slow rates of evaporation, it is going to, when all of those hydrogen bonds break and it turns from a liquid into a gas. What about the opposite? If it is really cold, and anybody who has had, any kind of ice in their drink, the ice is water, right? And you have a glass of ice water, and the ice is floating to the top. Why does that happen? Why is water's ice? You'd think if it's colder, it would sink because it would become more dense. But water is unique because it has that hydrogen bond lattice work that between the molecules, and when it's cold, instead of the heat breaking those hydrogen bonds, when it's cold, those hydrogen bonds become fixed. And so it forms this lattice work of the hydrogen bonds between the molecules. And so they become fixed and they take up more space as a solid versus a liquid, which is unlike a whole lot of other things. Usually when things become colder, they become more dense and tightly packed, but not water. Water becomes more dense and therefore it floats. So that's why ice is always floating on top of the surface. But if we were in Celsius and we were like right at 4 degrees instead of 0 degrees, four would be way at the bottom, where the coldest water is. But the colder it gets, the more it turns and eventually will form into ice, and that ice will float to the surface because of all of those different hydrogen bonds between the molecules. So those hydrogen bonds are going to account for the expansion of water when it's frozen. Those hydrogen bonds stay put. They don't break apart like if it's going to undergo evaporation when the energy is inputted as temperature rises. When the temperature is really low, those hydrogen bonds stay there and it forms the ice to float. So it has a high heat capacity. It takes a lot of energy to do this. It usually stabilizes a region. Anybody who has lived next to a large body of water may notice that the weather reacts a little differently. Some things behave a little differently when you live next to a huge, huge lake like that. If you live next to Lake Allatoona or Lake Lanier or one of the Great Lakes. My parents retired, moved out to Montana, and the lake in that valley is called Flathead Lake, and the weather is slightly different around that body of water simply because it takes so much energy to change the temperature of the water. So it acts as a heat sink. So again, water is cool, it stabilizes the temperature, and those bonds between the water molecules, those hydrogen bonds that we talked about, allow for something called surface tension. That's the last term on this page is surface tension. And so when those bonds are forming and breaking, forming and breaking, forming and breaking, when it's in the liquid form, those guys can keep the water molecules together to give it surface tension. And small objects like, do I have high heat capacity? Where's my picture? I don't have my picture. There it is. Here's a picture here about surface tension and small molecules, small objects like a needle, or if anybody has been out in nature and you've noticed bugs on the water, like water striders, they are gliding across the water because of this surface tension, because between the water molecules um, bonding and keeping each other together from those hydrogen bonds. So they are going to bind together and form surface tension. I've got a video here about water and space. It's really cool. I can't remember the name of that astronaut. He has a twin brother, but he's up at the space station. At least I think it's him. I may be wrong. But it's an astronaut at the space station, and he takes his water and he squirts it, into a paper towel. And then you can see how the water molecules react in space. And it's really cool to just look at it because it looks like jello, but it's not. And it's all because of the surface tension of water molecules. So check it out. It's not a long video. I think it's really cool. All right, so where were we? It stabilizes the temperature. It is a heat sink. Those bonds will break and evaporate. It takes a lot of energy to do that. The bonds will stay put if it's really cold, and that means that water will become dense when it forms ice, will become less dense. It will spread out when it forms ice, and that will float. Um, High heat capacity because of the hydrogen bonding. And again, it takes a lot of energy to change state from a liquid to a gas or from a liquid to freezing. That water is a huge heat sink. It's an excellent solvent. An excellent solvent. When you have these two terms, I'm definitely going to want y'all to know the difference between solvent and solute. So, solvent is going to be water. If we were in another class, maybe 1107, we talk about other elements that are great solvents, like alcohol is also another decent solvent. But water is a really good solvent because remember its shape that it was polar. It's a polar molecule. So it's going to have these slightly positive charges right over here and a slightly negative charge over here. And there are molecules, those hydrophilic molecules that we said will break apart in water. So those things that are dissolving in the water are called solutes. Solutes. So I have a saltwater tank at my house. And we have salt water and fresh water, and you have to clean the tank, you got to refresh the water, and you got to dissolve your salts in the water to make fresh water for my saltwater tank when it needs it. So here's your molecule of salt. Here's your sodium, here's your chloride, and remember those guys are, when they break apart, they become charged particles because they had that ionic bond. So sodium has, remember, this positive charge. It's hard to see in the picture, but it's there. And then chloride has this negative charge. And so these guys are ions, cations and anions, and they are going to be attracted to the water molecules. So here we mentioned in the very first part of the fact that water was polar and it can create hydration spheres. So that's what's happening here. We have our positive sodium and it is surrounded by the oxygen side of our polar water molecules because the oxygen side was the negative side of the polar molecule. Over here on our negative chloride side, they're going to be surrounded by water molecules as well. They're just totally hydrophilic process. And our hydrogens are positive. So the hydrogen side is facing this one, while the oxygen side is facing this ion over here. So solvent, water is an excellent solvent because it can break apart and it can break apart other molecules like salt, sugar dissolves in water, all sorts of things dissolve in water, right? Um, I am born and raised in the South and I like my sweet tea. So if I was, boiling my pot of water and the water itself is my solvent, and then I put my tea leaves, my bag of tea bag in there and allowed the tea, you put the tea bag in there and you can see the tea start to diffuse across the water. My tea bag, that would be the solute, while the water is the solvent. Um, my kids are teenagers and preteens right now. And a few years back, they were real big into the powdered stuff that they would add to their water, powdered crush, powdered Kool-Aid, whatever, in these little packets, right? And you rip off the end and you dump it in your water. The water is your solvent. The little packet of Kool-Aid or whatever it is that you're dumping in there, your vitamin water, whatever, you dump it in your little packet, that's your solutes. Know the difference between those terms. You'll probably have a question about that on the test, the difference between solvents and solutes. If I was asking you about the dried Kool-Aid that I add into my glass of water or my bottle of water before I shook it all up, the dried Kool-Aid would be solutes and the water is the solvent. So definitely let me know if you have any questions about the difference between solvents, water, and solutes, things added into the water. And a solvent isn't always water. Again, it could be alcohol or something else, but a solvent is going to be something that the smaller particles go and get dissolved into. Water is cohesive. It's all about those hydrogen bonds and them keeping that surface tension between the molecules of water. So with that surface tension, we're going to talk about how it will bond to itself and it will bond to other things. So when it bonds to itself, if you have, a chain of, there's water and here's another water, and it's bound to itself, water to water. That's cohesive. Cohesive is going to be water bound to itself. Back when we used to go to church pre-COVID, and we'd all, get together and be able to clasp hands. and shake hands and give hugs. I miss those. When you did that, and we used to hold hands, you would, go down the pew and everybody would hold each other's hand and you'd say the prayer. And of course, I realized that not everybody um, is the same religion as me or even religious at all. And that's okay. It's just my analogy that everybody is standing in a row and we're all holding hands and we're all people. So we're all the same. We're all bond together. That's cohesive. That's just like the water molecules. All the water molecules are touching nothing but other water molecules. But if the water molecule was touching something else. Like in this picture, the water molecules are touching the sides of that needle. That is adhesive. Adhesive. Cohesive, bound to each other, hand to hand, molecule to molecule. Adhesive, bound to something different, bound to something different. I have adhered to my Apple Pen. Um, you're bound to something different. If it was water molecules, when we get to 1108 and we start talking about plants and how plants undergo transpiration, they will pull the water up through their roots and through their vascular system, and it acts just like a straw. It's just like a straw that you're drinking from. The water molecules will stick to themselves, so they will pull each other up out of the ground and up through the straw or the water vascular system in the plants, in the xylem, and it will pull the water along together, together, together. All the water molecules together is cohesion. And then they will also stick to the walls of the xylem vessel in the plant. And when it sticks to the walls of the xylem, it's going to be adhesion, same as a straw. If you are drinking something out of a straw, I'm gonna drink some right now. I've got my straw and a sports drink that's not showing up right now, but you can see it. It's in there, and those water molecules are sticking to the side of my glass drink container. They're sticking to the straw. That's adhesion. So you might have a question about cohesion and adhesion in relation to water. The last thing I want to talk about in this video is the pH scale. Hopefully we have heard at least a little bit about pH before you've gotten to this level in school. But with the pH scale, it is going to be a measurement of hydrogen atoms. It's a measurement of hydrogen atoms, and it's logarithmic, meaning that it's going to move in the power of 10. It's going to move by powers of 10. And so hopefully we know at least what neutral pH is. And that is going to be the pH of pure water, pure distilled water, is at a pH of 7. This is neutral. 7 is neutral. And then we said that we are looking at hydrogen atoms and that they're going to be moving at a power of 10. So the more hydrogen atoms something gives off or donates, if it is a donor of hydrogen atoms, and again, hydrogen atoms, if we remember, proton and electron, and if it's lost an electron, it's a positive cation, right? So if you see this hydrogen and the hydrogen, there we go, our hydrogen has lost its electron, it's simply just a proton. So you may see it referred to as proton donors. We're still talking about hydrogens. That's what we're talking about. So as we move from 7 down to a pH of 0, we are becoming more and more acidic. These are acids down here. And every time we move down a number, this is going to be by power of 10, power of 10, power of 10, power of 10, power of 10. So by the time you get down to here, gastric acid is hydrochloric acid. Hydrochloric acid is very, very acidic. It's so acidic, this is your stomach acid. It can, anything with pH of 1 can potentially dissolve nails, metal nails. That's how acidic this stuff is. So your stomach acid is really acidic. If anybody's had heartburn, you know it's uncomfortable when that stuff tries to come back up. It's very acidic. So when it leaves the stomach, you need to buffer it. A buffer makes things closer to a pH of 7. No matter if it's a strong acid or a strong base, your body will buffer that stuff. But it does create the hydrochloric acid in the stomach, not only to help break down your food, but it's also a great immune defense. So that acid is a horrible environment for some pathogens out there. And so that takes care of some of those guys because they can't survive that acidity and they won't get you sick. So hydrochloric acid, pH of 1, super duper acidic. And again, if it is below 7, anything below 7 is going to be called an acid, and they are proton donors. They want to give away those hydrogens, just hydrogens like crazy. When they are in solution, hydrochloric acid in solution will break apart. Hydrochloric acid in solution will result in, here's our chloride, and here, no, here, here's my hydrogen. So if they break apart even Stevens, for every hydrochloric acid, there's going to be a one chloride and one hydrogen. It breaks apart even Stevens, and this is our hydrogen that we are donating, our proton donor. The further down the pH scale you get, the more hydrogens are going into solution when something breaks apart like that. So super acidic. If it is low on the pH scale, low numbers, that is acid. It's an acid. It is a proton donor. Hydrochloric acid is a great example of a proton donor. There are other things here in this list of other acidic things. Lemon juice, orange juice in the morning if you're having breakfast, tomato juice if you enjoy, spaghetti sauce and pizza and all of that stuff. That stuff's slightly acidic. It's a pH of 4. It's not crazy. It's not as crazy acidic as gastric acid, but it's still acidic because it's below a pH of 7, and that means it's acidic. And acids are going to be proton donors. You'll see hydrogens are giving away hydrogens. Those are proton donors. Even coffee and urine, depending on how your body's doing, and we'll talk about that in the next slide, can be acidic. Anything below 7. What about the other end of the pH scale? What if they're not donating protons when they break apart? What if they're keeping protons? What if they want the protons? If it's a molecule that wants to suck up all the protons, like maybe hydroxide, maybe they have this in their chemical makeup. And if we had a hydroxide and then here's hydroxide, and we added that proton to it, then what do we end up with? We end up with water. So that's the goal of these guys. They want protons. So these are proton acceptors. They want to collect the hydrogens. So on this end, these are base. These are called bases. You may also see them called alkaline. Alkaline. So if something is alkaline, it has a higher pH. It's going to be anything above a 7. So your body pH, regularly your blood plasma is 7.35 to 7.45. So if our pH is 7.35, that means it's above 7, and our bodies are slightly alkaline naturally. That's the way we are. As we go up, again, logarithmic power of 10, as we go up this pH scale, it's getting stronger and stronger and stronger, just like it did if we went down the pH scale towards the acids. If we go up the pH scale towards these strong bases, they get stronger and stronger. Bleach is a very strong base. If anybody has touched it, you're doing your laundry and you add in the bleach to your whites and you feel it, it's really slimy. Same for soapy water. You get that slimy feeling on your fingers. That's kind of a layman's test on, is this thing acidic or basic? Is that kind of slimy feeling that bleach gives off and some strong cleaners give off. They are alkaline or base. Don't let the name fool you, though. The first time I heard base, I was like, oh, that means the bottom number. It's a base and it should have a low pH. Don't get them mixed up. That is wrong, wrong, wrong. Bases are going to be at the top of the pH scale. Anything above 7 is a base, or it can be called alkaline. Whatever one helps you remember it better. But to me, I think base is slightly misleading because it makes me think of the bottom of the scale and not the top, but it is the top. Bases are above 7. And then our acids are below. So alkaline is going to mean the same thing as base. So these guys, maybe we had, let's use a base example. We have sodium hydroxide, and it's going to break apart in solution, just like we said our hydrogen chloride breaks apart in solution. So sodium hydroxide is going to break apart in solution, and it's going to break apart and form sodium, and then it's going to have hydroxide. So if we have hydroxide, that guy is a proton acceptor. It wants the hydrogen. So if we see something break apart like that and give off that, we know that is an example of a base. If we see something break apart and it results in a hydrogen, that guy is an example of an acid. So just in case on the test, if you are given an equation and you have something on one side, you will see an arrow and it breaks apart in solution, and here is your products at the other end of this reaction. What's the product? Look at the product. Is the product a hydrogen? If it breaks apart and it produces hydrogens or it donates protons, it's an acid every time. If it breaks apart and your products are going to have hydroxide, those guys are proton acceptors. They want the hydrogens. So if you see hydroxide at the other end of the products, then you are looking at a base, a base. So be able to know the difference between acids and bases, know what numbers they are, who's above 7, who's below 7, um, and be able to look at an equation, and be able to see, is this an acid or a base? What is it resulting in? What's the products produced? What are we looking at? Is it a proton donor or a proton acceptor? Something that is neutral, here's another video to kind of help us out on the pH scale here. Something that is neutral, again, is at 7. Your stomach acid, I said, was really strong. It's really strong, and we don't want it burning up your entire intestines on the way out of your body. That'd be terrible. So you need to buffer that. And how you buffer that, we've got a number of different buffers in the body, but one of them is bicarb. And so your food will come out, your intestines will secrete a hormone that tells your pancreas to release the bicarb, release the buffer, so we can get this really strong gastric acid somehow closer to this. We need to buffer. And a buffer will work for a strong acid and it can work for a strong base, but a buffer brings it closer to 7, to neutral. We want to try and neutralize whatever that strong acid or strong base is. So here, look at this over here. We have, this is bicarb right here, and here's a hydrogen. If we saw this in solution, um, and it produced bicarb and a hydrogen, it's a proton donor, right? So this is an acid. This would be an acid if it broke apart in solution. So that's exactly what this is. This is called, right here, this is called carbonic acid. And it is what we call a volatile acid because it breaks apart, and it can break apart and become different things. So carbonic acid is going to break apart. And when it breaks apart, it can break apart in different ways. If it broke apart and produced this with our bicarb and our hydrogen, that's going to be our acid. It's a proton donor. What if your body had a whole bunch of buildup of hydrogens and you were acidic? Your body takes care of that for you. Your body has 2 body parts that can help you fix your pH. It has chemicals that will do this, and it has your body parts, and that is your kidneys and your lungs. And so your kidneys are going to regulate your pH. It will make sure that you don't have too many hydrogens, and if your hydrogens are low, if you're alkaline, it will help you collect more hydrogens, and not urinate those out. We would keep those things. So your kidneys and your lungs are going to do something in just a second that we'll talk about. Those are the 2 physical buffers that your body has. And then we use chemical buffers um, that we can use to balance out stuff. So this is our bicarb buffer. We have our hydrogens. We're saying hydrogen is accumulating in the body. We're getting acidic, and we don't want to be acidic because we want to be at 7.35. So we have too many hydrogens in our body. We're going to attach them onto a bicarb, and then that is going to create carbonic acid. So we're going this way because we were too acidic. So now we have bound that hydrogen to a bicarb, and we have created carbonic acid. And now we are going to take that. So let's say we're at the side of the kidneys. Now we're going to take that and go shuttle this up to the lungs. And the carbonic acid at the lungs will break apart, where our water will stay and our CO2 gets exhaled out. And so that can help regulate our pH. And it all depends on what we're doing. We can exhale. The more we exhale, the more CO2 we release, and the more alkaline we become. We start climbing up that pH scale closer and closer to neutral. We may be over. If we are hyperventilating, for example, we may make ourselves too alkaline, and then we would need to reverse the process. We would need to slow our breathing down. So your body can absolutely regulate its pH. It does it all the time. You don't need to buy special alkaline water or any of the other gimmicks out there to help neutralize. Your body does it for you for free every day, 24/7. So we know about pH scale, understand the numbers of the scale. What number is an example of an acid? What number is an example of a base? Be able to understand what a proton donor means. It means when it breaks apart in solution, you're going to see hydrogens. If it is a proton acceptor, if it breaks apart in solution, you'd see something like hydroxide that is a proton acceptor. This guy is alkaline, and this is acidic. So please let me know if you have questions about acids and bases. Neutral pH is 7, and buffers are trying to get you there, whether you have a strong alkaline or you have a strong base and you want to get it back to the middle ground of a pH of 7. You don't want to move too far away from neutral. And this is another handy little website that you can check out about water and all the reasons why water is super cool. So definitely understand the pH scale, understand the many ways that water is awesome, that it's polar, that it's an excellent solvent, that it has a high heat capacity. All of the reasons why water is awesome are always going to be on the test too. That it's an excellent solvent, it's cohesive and surface tension, all those boldface terms from your outline. Know them, love them. You will have questions on those on this upcoming test.